Happy day and welcome everyone. Today's lesson is going to be on the kinetic molecular theory and effusion and diffusion, really focusing on effusion when we're talking about gas laws here. So the first thing says we first want to talk about the kinetic molecular theory. And anytime that you talk about a theory versus a law, they are a little bit different from each other, okay? So I have an easy way of remembering it. The word theory ends in what letter? If you said the letter Y, you're right, and it tells you why. So the theory is going to tell you why something is happening, okay? Now, the law, on the other hand, is not going to tell you why. The law is going to tell you what happens, okay? So the theory is proposing a reason for why something happens. And so what we do is, as scientists, as long as the entire community of scientists is agreeing on one particular theory, well, that's the theory of the day. But that could change, and you could have multiple theories about the same thing, okay? So until something is proven incorrect, then we accept these theories, okay? Now, the law is going to tell you, if I do this, this will happen, okay? And so that's how the law is going to be different when we talk about like the ideal gas law or the combined gas laws versus talking about something like the kinetic molecular theory, okay? So let's review some science terms. It says, we've stated Boyle's, Charles, and Gay-Lussac's laws. A scientific law summarizes the results of many observations and experiments, although laws do not tell us why. So a scientific theory explains why. The definition of a theory is a thoroughly tested model that explains why experiments give certain results. And so again, the easy way to remember it is that this ends in Y, in the letter Y, and so a theory tells you why. Why? Okay, so the kinetic molecular theory, what does it propose? Well, if we take a look here at this PhET simulation, what do we see? Well, we see these tiny particles, and what are these particles doing? I'm not changing anything. There's no battery here. It's not like there's like I had to plug this in or anything like that. But we can see that these tiny particles, and it doesn't actually even matter in what state of matter it is. It doesn't matter what state of matter, but they're in what we say is constant random motion. 3 times. Constant random motion. Constant random motion. Constant random motion. Okay, so it proposes that tiny particles in all states of matter, we do say all states of matter, are in constant random motion. So that's the kinetic molecular theory. Now, there are postulates of the theory. Here's the thing. In order to accept the theory, we have to assume some things. Now, not all of these things are completely true, but we have to make these assumptions in order to accept it. One thing is, the particles are so small, they're very tiny, compared with the distances between them, that the volume of each particle we can actually say is 0. And so we say that these are so very small, these tiny particles. The second thing is, well, we already said, the particles are in constant motion, and the collisions of the particles with the walls of the container are the cause of the pressure exerted by the gas. And so we can see, how do we know what the pressure is? Well, we know what the pressure is because they're exerting something on this surrounding, on these walls here, okay? Number 3, the particles are assumed to exert no forces on each other. They neither blank nor blank. Okay, well, this isn't totally true, but what we say is they neither attract nor do they repel. Now, we know they do. There are what are called IMFs, intermolecular forces, okay? And these IMFs, when the molecules come close to each other, if they have, one is more positively charged and one end is more negatively charged, we know that there are polar molecules. And so what ends up happening is they tend to stick, okay? And so we have different IMFs that do exist. Even if they are, let's say, noble gases. And we know that these are gases like neon or argon or helium or anything like that. We know that they don't like to bond. But they even have intermolecular forces. They're called London dispersion forces. And it's a temporary dipole that exists, very, very temporary, but it creates positives and negatives just from having a positive nucleus and negative electrons, and those cause attractions, okay? Or if you get two negative ends that come close to each other, what those should do is those should repel each other. We know that like charges repel, okay? But in order to accept this theory, this model right here, we basically have to say, nope, they're not attracting, they're not repelling. You can see here, they basically just bounce right off of each other, okay? Again, they're not really, and if you do zero in on one particular atom or molecule, you will see that sometimes they do slow down. Like if you look at the simulation, you will see that they do slow down, but overall we've got the same average speed of these molecules, okay? Now, this is really important. This is going to come up numerous times in this unit. The average kinetic energy of gas particles is directly proportional. It is directly proportional to the Kelvin temperature. Kinetic energy is simply the energy an object has due to its motion. Now, this is going to be really important, okay? The only time that the average kinetic energy will change is when we change the temperature, okay? So, we're going to say that the average, KE average, is dependent only on temperature. So when our temperature increases, that means that our average kinetic energy will be increasing. Okay? Now, you can zero in on one particular atom or one particular molecule, and you will see that the average kinetic energy of that particular molecule may be slightly different, but on average, we're going to say that they're the same. So, as a recap again, we're seeing it second time, very important. Molecules at the same temperature have the same average kinetic energy, no matter what the phase. Okay, so that means I could tell you that you have a tree. You have solid tree, okay? You have a cup of water, maybe it's lemonade, cup of lemonade, and then you have a helium balloon, okay? And the question is, if they're all at room temperature, I have them all in the same room, sitting on the same counter, which one has the highest average kinetic energy? Okay, now, if you're talking about speed, the speed of the molecules, yes, you would be right saying that the helium would have, the balloon of helium, those molecules have the greatest speed. They're in the gas phase, and those are the lightest molecules. But if I'm talking about average kinetic energy, as long as the temperature is the same, then they have the same average kinetic energy, okay? So one of the things that you'll see also if you end up taking physics, this equation is very common. So the average, or the kinetic energy per molecule of anything, or just kinetic energy, is equal to 1/2 mv squared. M is simply the mass, and V is simply the velocity. Now, this equation is on the equation sheet. This other equation, saying that the kinetic energy per mole is 3/2 RT, has been removed from the equation sheet, okay? And in chemistry, this is the one that we use all the time. Now, it is derived from the first one, and I'll show you that in just a little bit. But in this situation here, we use R for energy. And in order to use the one for energy, it's 8.314 joules per Kelvin mole, or per mole Kelvin, where T is simply the temperature, and we do that in Kelvin, okay? And so we can see here that using this equation, the kinetic energy, it doesn't matter if it's for a mole or for a molecule, it's only dependent on temperature. R is a constant, okay? So let's take a look here and see. So again, when we talk about speed, we do say that if it's a lighter molecule, you can see that these red molecules are lighter. They are moving faster, okay? Definitely moving faster. But when you talk about average kinetic energy, the average kinetic energy of both of them, if the temperature is the same, which both of them are at 300 Kelvin, then the average kinetic energy is the same, okay? Now, if we look at the equation sheet here, we can see that they are giving us the kinetic energy equation, but only 1/2 mv squared, okay? And again, this doesn't really apply in chemistry. It's what they have derived from this equation that actually matters. And I'm going to tell you how it makes a big difference, or how it can make a big difference if you're going to solve some problems, okay? So we'll get back to that in just a little bit. All right, so effusion and diffusion. Gases will spread from areas of high concentration to areas of low. We know that that's called diffusion. And diffusion is a term used to describe the mixing of gases. When a small amount of perfume is sprayed, it takes some time before all the people in a class smell it. And the rate of the mixing of gases is simply called the rate of diffusion. That's it. It's the same thing. Now, there's a Scottish chemist by the name of Thomas Graham. He worked in the 1840s on this, and he's working on measuring the rates that gases escape through a tiny hole in a container. This is now called effusion. So just slightly different here. He noticed a trend based on the molar mass of the gas. What he found was, if there was a lighter gas with a lower molar mass, then it would actually effuse faster. The faster it would effuse. Okay, now, I want you to imagine this, okay? So, me as a human, I can get through that door, okay? So I can walk through that door pretty easily. And if I had a whole bunch of humans in here, we could all get through that door pretty easily, okay? Now, if I had something like a giraffe, and there were a whole bunch of giraffes in here, okay, and the giraffes are trying to exit through the door. Now, gases and us, we're made of molecules, okay, so we're made of atoms and molecules. And similar to those, we want freedom, okay? Everybody wants freedom. The gases want freedom. So if there's a hole, they're going to try to leave. They're like, woohoo, freedom, okay? So if the door is open, who's going to have an easier time getting out? Well, we pretty easily can just kind of make it right through the door. The giraffe is going to have a lot harder of a time making it through the door, okay? So it's going to have to lower its neck and really kind of shimmy, and it's probably going to be a lot more mass. So we find the same thing with these gases, okay? And so if you have a balloon, for example, and it's full of a mixture of gases, you can even put air inside of there, what they have found is the lighter molecules effuse faster, okay? But it's not a complete direct relationship. What they found was, or inverse relationship, what they found was it was inversely related, but according to the square root of the mass, okay? And so I wanted to show you mathematically because they did remove this equation from the equation sheet as well, but it's so easy to use. And again, I just wanted you to get an idea of how simple the math is and how it works, and also to remember that it isn't exactly opposite. It is inversely related, but not exactly inverse, okay? So I wanted to show you that. All right. So when we look at his equation, what he did is he said it states that the rate of diffusion of a gas is inversely proportional to the square root. That's important. So to the square root of the gas's molar mass, okay? And you do have to square root the molar mass, not the rate. So you have to be careful with this. So R represents the rate in volume per unit time, and M represents molar mass, grams over moles, okay? So grams per mole. And so normally, if we don't know what the molar mass is, we do that. We do grams, moles, grams over moles. But in this particular problem, you don't need to be able to do that. So they are going to ask you sometimes, what is the molar mass of the unknown gas, okay? And so you can just use the rates and use the ratio. That's all we're doing is we're using a ratio, okay? So this first question says, calculate the ratio of velocity of helium to neon at the same temperature. Now, most people will look at a problem like this and say, I'm so confused, there are no numbers. That's right, there are no numbers in this problem. And then they're done. They think that they're done. Okay, they're like, I can't calculate it. Yes, you can. So if we know what the elements are, we know that it's helium to neon. Now you have to be careful with this. When we do this, I want to make sure that I'm not writing the molar mass of helium over the molar mass of neon. That's opposite. So be careful. What I want is, if I want helium to neon, then what I want is I want the rate of helium over the rate of neon, which means that's equal to the square root of the opposite. So you can see that if 2 is down there, then its molar mass is opposite, okay? So the molar mass of neon, I look on the periodic table, and it's 20.1797, okay? So we're going to go with 20.18. Okay, and that's grams per mole. And then we also need to write the opposite, which is helium's molar mass. And so helium is 4.0026. We're just going to go with 4.00. And again, that is grams per mole. Okay, now, you're looking at this and you're thinking, wait a minute, I don't know either of the numbers on the left. Right, and that's great because we just want the ratio of it, okay? So let's do this calculation real quick here. And I just got 2.246. With 3 sig figs, that's 2.25. Now, you can either write it as 2.25 over 1. It's 2.25 to 1, okay? So that means that this is the rate of helium versus neon. Does it make sense? Yes, helium's lighter. Helium should be fusing at a faster rate, okay? So you always want to make sure that it makes sense. The lighter the gas, the faster it's effusing, okay? So if you do it backwards, you'll know. And by the way, remember, all you have to do here is just don't forget to use parentheses. So I had to do square root parentheses 20.18 over 4, okay? Or you can do the square root of both of them, but just make sure you're dividing. So pretty easy there. Okay, question 23. An unknown gas effuses at a rate 0.468 times that of oxygen at the same temperature. What is the molar mass of the unknown gas? Okay, so you can set it up differently. It totally doesn't matter. But the way that I want to set it up is I know that my ratio, it's 0.468 over 1. Okay, it's 0.468 over 1. So just kind of keeping that in mind, that that's how I want to do this. And so it's 0.468 that of oxygen. Okay, so that means that if I call oxygen 1, then that must be at 0.468. Okay, so let's set up our equation here. So the way I'm going to set this up is I'm going to say the rate of my some unknown. You can use a question mark, you can use X, whatever you want. And that is over the rate of my oxygen of O2. Okay, and that's equal to the square root, and so then oxygen is going to be opposite of this, so I'm going to do the molecular weight of oxygen divided by the molecular weight of question mark. And so now let's fill this in, okay? So I know that it's going to be 0.468 over 1, or just 0.468, is equal to the square root. Now, do I know this? Well, yes, I know the molar mass of oxygen. It's 32.00 grams per mole. And then I'm going to divide it by X. Okay, now, if you remember from algebra, from your math class, if you want to get rid of the square root, what do you do to both sides? Well, if you square it, you can get rid of the square root. So what I'm going to do is I'm going to square this, which means I'm going to need to square this. So if I get 0.468 squared, that gives me 0.219. And so I have 0.219 is equal to 32.00 over X. Now, easy algebra, I call it the swap thing. And so my swap thing is I can just switch those two to solve for X. And so then I'm just doing 32 divided by my answer. And I get 0.219. I get 146.11 or 0.12. So I'm just going to go with 146. So X is equal to 146 grams per mole. Okay. So does it make sense? Yes, it should make sense, because if it's effusing at 0.468 times that means of oxygen, that means that it's effusing at a lot slower of a rate. Now, again, it's not that it's going to be, so we know it's going to be have a heavier mass. So oxygen weighs less, but it's not, half, and so you would say double the mass because of the square root that ends up throwing it off. Okay, so just keeping that in mind. All right. Last question here. A container of nitrogen and carbon dioxide is found to have a tiny hole. If the CO2 is effusing at 24.0 milliliters per minute, what should be the rate of effusion of the nitrogen gas? Okay, so we are specifically looking for the nitrogen gas. So again, it doesn't matter how you set it up as long as your molar mass is going to be opposite in this situation. The only time it really matters is if they're asking you for the ratio and they say of this to this, okay? So I'm just going to do the rate of nitrogen and the rate of carbon dioxide is equal to, so remember, I have to make sure that I get my CO2 on top and then my nitrogen on the bottom for the molar mass, and that's the one under the square root. Okay, so let's put in what we know. I know I'm looking for my nitrogen's rate. I know that CO2 is effusing at 24 milliliters per minute. That's equal to carbon dioxide. If I added up 12.01 plus the 32.00, then I am going to get 44.01 as my molar mass, so my grams per mole for CO2. And then I'm going to divide that by nitrogen, which we know is nitrogen's 14.0 times 2, so I'm going to get 28.00 grams per mole. And then don't forget to square root. Do not forget to square root. Okay, now, I would not square both sides. So a lot of times AP students will want to square both sides. Don't do it. If you do that, you're going to get R squared, okay? So all you're going to do is just plug the number into your calculator. So what I'm getting is R of nitrogen over 24.0 is equal to, so let's plug this right in. I'm going to do the square root of parentheses 44.01 divided by 28 end parentheses, and that gives me 1.254. So let's just go with, 1.254 with 4 sig figs. And now to get N2 by itself, I'm just going to cross multiply. So I'm going to multiply my answer by 24, and I get 30.08. So my Rn2 is equal to 30.1 with 3 sig figs. And this is, again, in the same units, so milliliters per minute. And again, you always want to make sure that it makes sense, okay? So we know that nitrogen is lighter, and if it's lighter, it should be effusing at a faster rate. So if we know that the CO2 is effusing at 24 milliliters per minute, it does make sense that the nitrogen is going to be effusing at a faster rate, okay? And that's it for effusion and the kinetic molecular theory. And we'll come back and we'll talk about the root mean square velocity in just a little bit here. Happy day, everybody.